So these are the invariants. And so for this part A, what's different about these two graphs that's going to stop it from being an isomorphism? So many different ways you could do it, but I noticed that this has 7 edges and this has 8 edges. So there's no way there's going to be an isomorphism. So that's called the invariant. And then this one here, this is a vertex of degree 4, and there's no degree 4 vertex here. So you can't make degree 4 vertex here. So you can't make an isomorphism. So that's called the invariant. All right, so let's see. Are these two graphs isomorphic, or is there an invariant? And same with this one. So if we start off by just counting the vertices, looks like there's 4 vertices on both, 4 edges on both. So I'm just going to start. It's not always that the vertices and the edges are labeled, but this one they are, V2, V3, V4. And then W1, W2, W3, W4. So let's just start with these. So V1 is a vertex of degree 1, so that's got to be W4 there. And then V2 is a vertex of degree 2, so that's got to go to the W3. And then V3 has degree 1, 2, 3, so that's got to go to W2. And then V4 has got to go to W1. Okay, so we got the edges, or the vertices. So next we work on the edges. So E1, E2, E3, E4, and then F1, F2, F3, F4. So edge 1 is on the vertex of degree 1 and the vertex of degree 2. So that's going to be that F4 right there. And then E2 is going to be on the next one, right? So that's going to be the F3. And then E3 has got to be the F1. And then E4 has got to be the F2. Okay, so if I look at these two graphs, I'm always going to start off by looking at number of vertices or number of edges. And I notice this has 5 vertices, and this has 6 vertices. So it cannot have an isomorphism because it's got an invariant. All right, let's look at this one here. They look pretty similar, but if I'm looking at circuits, so this is a circuit of length 3, right? 1, 2, 3 edges to get to that circuit, and there's 2 of those, right? Two circuits of length 3 in G, right? Okay, do we have that in here? No, there's no circuits of length 3 in G prime. So that's the invariant. Okay, so how about this one? If I unfold this, I think, because it's all connected, so I think I'm just going to start like here to here. So if I say, okay, the vertex A matches up with the vertex T, and then that would mean the vertex C would match up with the vertex U, and then the vertex E would match up with the vertex V, and then moving on to G, that would match up with the vertex W, and then B would match up with the vertex X, and then D would match up with the vertex Y, and then here I get to Z, oops, where am I at? D goes back to the vertex F, right? F to Z, and then look at that. I get back to A, or I get back to T. So this is isomorphic. So I've found a relationship between the two graphs and their vertices. So isomorphic. Okay, this one, it's very kind of similar to this one, but can you see that this one is not connected? And this one is connected. And so for sure, that's going to stop you from finding any isomorphism, because that is an invariant. Okay, so non-isomorphic graphs of 3 vertices. So, here we go, simple. So that means no loops, no parallel edges. So there's really not too many. Doesn't say how many edges, so I'm just picking out 2, 3, and 1 edge, and that's it, right? Okay, so this one here, non-isomorphic with 3 vertices. Okay, so we got this one, and then we've got one with an edge just between 2 of them, and then we've got an edge between both of them, and then we could have one with a loop and one with an edge between the 2, and then we could have a loop and just a single vertex. I could have parallel edges and a single vertex. I could have a loop on that end, and then a vertex here. And then I could have 2 loops on one vertex and 2 isolated. Or I could have 1 loop and then 2 isolated. So those are all the non-isomorphic.